students, I hope this video finds you well. In this video we will be handling tutorials on modeling the frequency domain and time response, and this video is made for both Pretoria and Emala Clinic students. So before you join this tutorial, make sure you go back to the video slides prepared by the Pretoria lecturer, Mrs. Klungulu. Make sure you listen to them first before joining this tutorial. Although where I'm starting today is what we have done in class before, but I just choose to start here so that I can key you in, so that the next of the chapters we'll be doing, it won't be a problem because I think this is a foundation of control system. If you can learn how to model in the frequency domain and then how to analyze the time responses, then you should be able to move ahead with the rest of the chapter. So I decided to start here again due to the lockdown. So let's start. I have two tutorial questions to solve, and I wouldn't like this video to be very long, so we'll move as quick as possible. So if I'm running very fast, you are free to pause the video at any time and listen again as to what I did. So you don't need to complain, just pause it. It's your video. Once it's downloaded, once it's uploaded in my tutor, it's your video. You can visit at any time. Okay, number one question says, given the following differential equation, solve for y of t if all initial conditions are 0. So, and the hint is given to you to use Laplace transform. So let's start. I assume that you know, but let me remind you again. So this equation is in time domain. So let me just set up my pen and then we move on. Okay, so the question is in time domain, equation is in time domain. D squared y dt squared plus 12 dy dt plus 32 y equal to 32 u of t. So now to solve for y of t, this y of t, this one here, is in time domain, but we have to move from time domain to frequency domain and then use partial fraction to come back to time domain in order to get the output response, which is this y of t. So that is one of the reasons, or one of the importance of modeling the frequency domain. So let's start. So if we were to consider initial value, which we don't need, this first one would have been capital Y S x squared here. Sorry, I have to shift it a little bit. S squared here plus, now the first order, this is second order, the first order, y of 0 negative, so plus, so that we know this system was once at initial condition of first order and also at initial condition of 0 order. So we don't really know the initial condition as 0 order and the initial condition as first order, so we are going to ignore those things and we'll just move into the present condition of the system. So in other words, ignoring the initial order, we will just have to move to the first order, which is 12 dy dt. So that one should give us 12 dy dt should give us 12 s y of x. Then this one is plus 32. Remember, it's now capital Y, not small y, of x equal to, now 32. Remember, unit step function, this is 1 over x, so it's 32 over x here. Okay, so if we factorize the output response, which is y of x, then we have here x squared plus 12x plus 32. enclose equal to 32 over 8. So that means the output response y of x is equal to 32 all over s into x squared plus 12x plus 12x plus 32. So this is the output response in frequency domain. So we have achieved something by transforming the system from time domain to frequency domain. But you look at the output response is in frequency domain, but we need it in time domain. So that is where partial fraction comes into play. So if we must use partial fraction, we have to remember the definition of partial fraction. So since we have a quadratic equation here, it's a second order, so we have to check whether the roots are real. So if you check whether the roots are real, we find two numbers. You have different ways of doing it, but just to save time, find two numbers. When you multiply them, you get the last term. When you add them, you get the middle term, and those numbers are what? 4 and 8. 4 and 8. So we have this, so that you have 4 times 8 is 32, then 4 plus 8 is 12. Fine, so we are there. So we now have a new equation because we need partial fraction. Now have a new equation of y of x equal to 32 all over s into s plus 4 s plus 8. So in this case, we remember that this is equivalent to k1 over s plus k2 over x plus 4 plus k3 over x plus 8. So this is how partial fraction will help us. This is definition of partial fraction if you have a system of equation like this. So this is how you define it. So if we can solve these three constants, k1, k2, k3, then we can easily use a table in the slide that Ms. Chungulu already explained, and then we can just use it to choose what does the constant, for instance, the constant over s over 8, what does it stand in, how does it stand in time domain. So to do this, we solve for k1. So k1 equal to everything there, 32 all over. Now the denominator of k, we are going to remove it because it's going to be equal to 0. So we remain s plus 4, the denominator of k1, sorry, because we have k2 and k3. Okay, so now this is as that complex form goes to 0, so which is this one. Okay, I know you know. All right, so here we have 32 over, if s goes to 0 and s goes to 0, we remain 4 times 8 is 32. So, and 32 over 32 is equal to 1. So k1 equal to 1. What about k2? So we check for k2. K2 equal to, now bring back the whole equation and eliminate the denominator of k2. So we have x into s plus 8. So now as s tends to minus 4, because the solution for the denominator of k2 is s equal to minus 4, just like that one was s equal to 0k, you know that. So now here we have 32 over minus 4 into minus 4 plus 8, because anyway you find s, you are going to represent it, replace it by minus 4, so which is equal to 32 over minus 4 plus 8 is 4 times minus 4 is minus 16. So here we have minus 2. So similarly for k3, K3. We do the same thing, 32 over x into x plus 4. So we eliminate the denominator of K3. So as s tends to minus 8 is equal to 32 over, now we have minus 8 into minus 8 plus 4. Okay, so this is equal to 32 over, now 4 plus minus 8 is minus 4 times minus 4 times minus 8 is 32. So this is equal to 1. So at the end of the day, we have K1 equal to 1, K2 equal to minus 2, and K3 equal to minus 4. Sorry, equal to 1. Where did I get a minus 4 from? I'm thinking something else. That could be the problem. Okay, fine. Then we now come back to our equation. So the output response y of x becomes 1 over s minus 2 over s plus 4, then plus 1 over s plus 8. So if you take the inverse Laplace transform of this, you don't need to start doing your Laplace transform formula. Just go back to the table in that chapter 2 of modeling the frequency domain and see that a unit step represents 1 over s, and then exponential decay represents, if you have a denominator of a negative solution, that is x plus a, or and so on and so forth. So if it is like that, we have, for the unit step, we have 1, then minus, this is a coefficient, the numerator 2. Then you look at the denominator, that is 1 over s plus 4, which is exponential decay of negative 40, because here 4 is positive but the solution is negative, you know, from quadratic equation. Then plus, remember that this one is just 1, so the coefficient is 1, so we have exponential negative 8, the same thing. Then u of t, yes, so this is u of t, 2 exponential negative 4 u of t, and exponential negative 8t u of t. Sorry, it's a mistake. So this is the solution, or this is y of t. Why did I say y of x again? This is y of t, okay, because it's now in time domain. And if you go back to our question, this is what we want to get. Further analysis can ask you which one is a forced response and which one is the natural response. And we all know that the natural response of the system is the exponential rise and decay part of it, and the constant term is the input. So which is, of course, the input is unit step, so unit step is t here, so everything are represented. So this is actually the natural behavior of the system, how it behaves at rest. So but when something biases the system, like a unit step or ramp or whatever input you want, then things can change based on the input. Okay, so that is by the way. So let's go back to number 2. Remember, before we move, that in partial fraction, this method I use is not always. There are a lot of methods, so anyone that is better for you to use or you understand better, then don't hesitate to use it. So okay, let's come back to number 2. Number 1 is done. So number 2 says determine the transfer function t of x from the control system circuit shown below. So this is just like in engineering 2, is an RLC circuit, so it's not really too complex. but I chose this circuit to give you the a kind of foundation, so that when you see complex circuit like the 3 loops, the 2 loops, and so on, it won't be too tedious for you. So I should have maybe chosen to start with 3 loops, but I said no, let me carry everybody along. So let's start with this single loop RLC and take the output voltage as a response from the capacitor. So if we do that, then we check the order of the system. Is it first order, second order, third order? Otherwise, if it is second order, what is the natural frequency? If it is a third order, can you approximate to second order and see, find the natural frequency, damping ratio, and the nature of the damping? Then will you be able to evaluate the rise time, peak time, settling time, and overshoot? Okay, let's see the system. So first of all, we have to calculate the differential equation. We have to start in time domain. Don't jump to frequency domain. Sometimes you may lose mark. I know you know how to go straight to frequency domain from that circuit. It's very easy, but let's start with time domain. The input voltage, according to Kirchhoff voltage law, is the algebraic summation of the voltage drops across the circuit. So that means we have the voltage drop across the resistor, we have the one across the inductor, remember, and then we have the one across the capacitor. So now this is the equation of the circuit. Okay, we don't have the second equation, so no need of labeling it. So now from here we use Laplace transform and transform them to frequency domain, so which the voltage remains the voltage input, frequency domain, the resistor constant, then current becomes capital letter in frequency domain, plus now inductor with the differentiator S has to come in, and then the current there in frequency domain, and then plus 1 over CS, then on the current. You are done. So the equation have been transformed from time domain to frequency domain. Okay, so now what we have to do is to determine VO, the output voltage, over the input voltage. So this will give us the transfer function of the system. So that is the next target. So this one is the easiest of all that you can do, but it's a foundation. So maybe next tutorials or questions we can bring up a circuit, whether it's 4x4 whatever, and solve it, or 4 loops or 3 loops or double loop, anyone we can still solve. Okay, fine. So that means this VI of X is equal to, now I'm factorizing the current, so this is R plus SL plus 1 over CS. So now I remember that we said that we are going to measure the output voltage as the voltage appearing in the capacitor, and the voltage appearing in the capacitor, capacitive voltage, is equal to the capacitance of the capacitor in frequency domain multiplied by the current, just like Ohm's law. Ohm's law that says V equal to what? R. So that means in frequency domain, if you represent the capacitor like this with a complex S, it will act just exactly like the resistor. So what you are just doing here is Ohm's law. It's nothing else, nothing more. So this is a state in which the capacitor behaves like a resistor, and for inductor, once it is like this, it will behave like a resistor. Okay, that's by the way. So that means I have to find a way of getting something like this from my equation. So getting I of X over C of S. So if I looking at the condition of my equation here, I will just remove this from the bracket. So to remove 1 over CS from the bracket, I'm going to have VI equal to I of x over CX into now RCX plus S squared CL, it's just the same, plus 1. So I've removed this 1 over CS from the bracket and it's out here. So, and I remember quickly that this is equal to my output voltage, so it changes to output voltage. So I have VI equal to output voltage into this RCS plus CL S squared, that's the correct way, plus 1. Okay, so having done this, I'm going to express that the output over the input, which is equal to 1 over, let's start with CL now, the highest order, CL S squared plus RCS plus 1. So this is like just saying cross multiply. This one comes down here and this one goes down here, so it's just cross multiply, so it becomes that. So yeah, that's what we have here. So, and this is equal to, now remember that I told you in class, and of course in Pretoria, Mrs. Chungulu might have told you, for you to actually determine the output response or the transfer function time response of the system, you have to leave the highest order to have a coefficient of 1, and that we call it what? Monic form. So we have to leave this in monic form. So to leave it in monic form, we are going to remove these coefficients here, CL. So to remove it, we divide everything, both the numerator and the denominator, by that CL. So we have here 1 over CL all over S squared plus, now RC over CL is R over L S plus 1 over what? CL. So we are done. At this point, your system is what? A monic form. Okay, so now we remember that from the circuit, let me just go up from the circuit, that R is 0, 1, 0, 2, I think this mistake there, 0, 2, and then H is 0, 1, and this one is 0, 4, not millihenry, just Henry and Farad and ohms, just for the example, for the purpose of the example. Okay, fine. So we said things are equal to 0, 2, L equal to 0, 1, and C equal to 0, 4, Farad, Henry, ohms. Okay, now that means R over L equal to 0, 2 over 0, 1, which is equal to 2. Then L1 over LC, which is equal to 1 over 0, 1 times 0, 4, which is equal to 1 over 0, 4, which is equal to 100 over 4 equal to 25. Yeah, okay, so that means now we come back and replace our equation. Let me just move a little bit higher. Okay, go up a little bit. So now our transfer function T of x becomes 25 all over S squared plus 2x plus 25. Wow, what a great achievement. So we've been able to see the transfer function of that circuit Now control system starts from here, so we can quickly say that the system is what. So to answer our question A, it takes a second order system. It's a second order system. So therefore okay, let's go to B. It's fine. So this one takes evaluate the natural frequency. So natural frequency, what is it? If you remember in the slide that we define it for second order system, we define the transfer function to be natural frequency squared x squared plus 2 natural frequency multiplied by the damping ratio x plus natural frequency squared. So that means here natural frequency equal to what? Root 25, which is equal to 5 radians per second. So that means 2 natural frequency and the damping ratio is equal to 2. So to cancel 2 here, 1 from here. So what we are doing, we are taking the coefficients and equating it to the coefficient of our transfer function just to solve for those parameters. So if this one is equated to this and this one is equated to this, that's what we are doing. Okay, so that means natural frequency, which is 5. So we have here 5 damping ratio equal to 1. So therefore the damping ratio equal to what? 1 over 5. And 1 over 5 is what? 0,2. Remember, it's dimensionless, it's just a ratio. So from 0,2 we now pause to answer the next question. Let's go back, let's go up a little and see the question. Here it says, here it says the order of the system we've solved, then the natural frequency, the damping ratio, and the nature of the damping. Okay, before we evaluate the rest. So the nature of the damping, if we look, because the natural frequency is 0,2, so we quickly remember that it is under 1, is lower than 1. So if it is lower than 1, that means it's under. So that means the damping is what? Under. Did I say under 1? Under damped. So I usually use this to remember it those days. So it's under damped. Under damped system. So that's the answer. So because it's under 1. So but if it is above 1, it's over damped. So if it is equal to 1, you can't be equal to your master. It's going to be critical. You are going to be in loggerheads, so it's critically damped. But if it is 0, that means you didn't even come at all. It's undamped. There's no damp there. So just for you to remember, so once it is below 1, from 0,1 to 0,99999, it's under damped system. So now I would like you to take this formula here. Let me just show you. You have the slide, of course. So plug in your values here to calculate the rise time, peak time, settling time, and overshoot. Keep practicing. So we are going to stop this video here, and the next time we'll try to see block diagram reduction and signal flow. So I thank you. Make sure you, before you listen to this video, that you might have listened to the PowerPoint videos uploaded by the Pretoria lecturer. Alright, so thank you.